Hello, and welcome. Perhaps you're lying in bed right now, or maybe you've found a quiet corner of the evening. Either way, this is a space for us to drift together into something curious and calming. There's a question that lives at the edge of sleep, in that soft territory between wakefulness and dreaming. It's the question of whether this moment, right now, as you settle into stillness, might be unfolding differently somewhere else. Whether another version of you, in another version of now, made a different choice tonight, stayed awake a little longer, chose a different room, a different thought, a different breath. It sounds like fantasy, doesn't it? The stuff of science fiction and late-night wondering. But here's what's remarkable. Some of the most brilliant physicists of our time have spent decades exploring the possibility that parallel worlds aren't just imaginative speculation. They might be woven into the very fabric of reality itself. We don't need to rush toward answers. There's no urgency here. No pressure to solve anything. What we have instead is an invitation to explore an idea that sits at the intersection of the smallest things we know and the largest things we can imagine, to wonder about the nature of existence itself, and to do so gently, with curiosity as our guide. You might feel the air around you right now, the temperature of the room, the weight of your body wherever you're resting. This felt experience seems singular, immediate, undeniably here. And yet, beneath the surface of ordinary experience, reality behaves in ways that challenge everything we assume about the world. Tonight, we'll travel together through landscapes of possibility. We'll visit the quantum realm, where particles exist in multiple states at once, and we'll peer toward cosmic horizons, where space itself might extend forever. We'll consider what it means if every choice you've ever faced created a branching path, with all versions of the story unfolding simultaneously, in realms just beyond perception. But we'll do this slowly, contemplatively, with the understanding that mystery isn't something to conquer, it's something to appreciate. The goal isn't certainty, it's wonder, and perhaps in that wonder, a kind of peace. So settle in, let your thoughts become fluid, and together, let's explore the extraordinary possibility that parallel worlds may be closer than we think. Building from that sense of settling in, let's begin with something you've probably experienced. A moment when reality feels slightly off, slightly thin, as though you're brushing against something just beyond the ordinary. Have you ever walked into a room and felt certain you've been there before, even though you know you haven't? That uncanny sensation of déjà vu, where the present moment seems to echo with impossible familiarity. Or perhaps you've had those moments of decision where you felt the weight of multiple futures pressing against each other, turning left or right, speaking or staying silent, as though the universe itself was holding its breath, waiting to see which path you'd choose. These experiences feel meaningful, don't they? Like glimpses through a veil. Most of us dismiss them as tricks of memory, neurons misfiring, the brain trying to make patterns where none exist, and perhaps that's all they are. But there's something worth considering here, something that connects human intuition to the deepest puzzles of physics. In the realm of quantum mechanics, the science of the incredibly small, particles don't behave the way we expect solid, definite things to behave. An electron, for instance, doesn't exist in one specific place until we measure it. Before observation, it exists in what physicists call a superposition, multiple states at once, multiple possibilities held together in a strange kind of limbo. It's not that we don't know where it is, it's that it genuinely isn't anywhere specific until something forces it to choose. This isn't philosophy. It's verified, repeatable, experimentally confirmed reality. The subatomic world operates according to rules that feel alien to our everyday experience. Rules that seem to say, definiteness is an illusion, multiplicity is fundamental. Now, stretch that idea upward. If the building blocks of reality exist in multiple states simultaneously, what does that suggest about the larger structures built from them? About molecules, cells, bodies, decisions, worlds? Perhaps our intuition isn't entirely wrong. Perhaps those moments when reality feels thin, when other possibilities seem to shimmer just out of reach, we're brushing against something true, not mystical, but physical, not supernatural, but natural in ways we're only beginning to understand. The boundary between what is and what might be may not be as solid as we've assumed. On the contrary, at the most fundamental level, that boundary appears to be extraordinarily fluid. The universe, it seems, has been holding multiple stories all along, and we're just beginning to ask what that might mean. From that fluid boundary between possibility and actuality, let's turn our attention to something deeply personal, the paths we didn't take. Think back to a significant choice in your life, perhaps a job offer you declined, a conversation you decided not to have, a city you almost moved to but didn't. In the aftermath of such decisions, we often wonder, what would have happened if I'd chosen differently? We imagine alternative timelines, sketch out the rough contours of lives we didn't live, and then we let them go, accepting that we can never truly know. But what if we're wrong about that finality? What if the fork in the road never actually closed? In 1957, a young physicist named Hugh Everett III proposed something radical in his doctoral thesis at Princeton. He was trying to solve a problem in quantum mechanics, the same mystery we touched on earlier about particles existing in multiple states. The standard interpretation said that when we observe a quantum system, the wave of possibilities collapses into a single outcome. But Everett asked, what if it doesn't collapse? What if all outcomes happen? His answer became known as the many worlds interpretation. According to Everett's mathematics, every time a quantum measurement occurs, and these occur constantly, trillions upon trillions of times per second throughout the universe, reality branches, not metaphorically, not in our imaginations, actually branches, creating parallel worlds where each possible outcome unfolds. In one world, the particle spins up. In another, it spins down. Both worlds are real, both continue forward, and crucially, neither is aware of the other. Now, if this is true at the quantum level, the implications ripple outward in staggering ways. Every quantum event in your brain, and there are countless such events occurring constantly, as neurons fire and chemical bonds form and break, would create branching realities. In some branches you chose the job, in others you declined. In some you had the conversation, in others you stayed silent. This isn't mere speculation about choices as metaphors. It's a suggestion that the universe has a mechanism built into its fundamental physics for making all possibilities actual. Everett's idea was largely ignored during his lifetime. It seemed too extravagant, too ontologically lavish, but in recent decades, it's gained serious traction among physicists, not because it's comforting or intuitive, but because it's mathematically elegant and solves certain problems that other interpretations struggle with. Whether it's true remains an open question, but the possibility it raises is profound, that nothing is ever truly lost. Every version of every story unfolds somewhere in the vast structure of reality. The paths you didn't take might still be unfolding, walked by versions of you in worlds just beyond the reach of perception. So here we are, standing at the threshold of something vast. We've touched on quantum strangeness, on the physicist's suggestion that reality might branch with every measurement, on the haunting possibility that parallel versions of ourselves might exist beyond an invisible veil. It's a lot to hold. And before we go further, it's worth pausing to set some gentle expectations for the journey ahead. This isn't a quest for absolute answers. The nature of parallel worlds, whether they exist, how they might work, what they mean, remains one of the deepest open questions in science. Many brilliant minds have spent careers exploring these ideas, and they still disagree. Some embrace the many worlds interpretation with confidence, others find it unnecessarily extravagant. Still others propose entirely different frameworks for understanding reality's multiplicity. What we're embarking on tonight is an exploration of possibilities. We'll encounter ideas that are grounded in rigorous mathematics and experimental physics, but we'll also venture into territory where science blends with philosophy, where questions outnumber answers, and where wonder becomes the appropriate response. There's a certain comfort in not knowing, if we can learn to sit with it. Our minds often crave certainty, neat conclusions, problems solved and filed away, but some questions are too large, too profound, to admit simple resolution, and perhaps that's okay. Perhaps the questions themselves are valuable, regardless of whether we ever find definitive answers. Consider how this inquiry makes you feel. Does the possibility of parallel worlds bring comfort or disorientation? Does it make existence feel more meaningful or less? There's no correct answer. Different people respond differently, and those responses can shift depending on the day, the mood, the hour of night. What we'll aim for is balance, curiosity without anxiety, intellectual rigor without exhaustion, speculation grounded enough to feel plausible, but open enough to preserve mystery. We'll move through landscapes of physics and philosophy. We'll examine evidence, such as it is, and acknowledge its limitations. We'll consider what parallel worlds might mean for identity, choice, and meaning. And we'll do all of this at a pace designed not for information extraction, but for contemplation. Think of this as a conversation rather than a lecture. We're wandering together, exploring together, holding ideas lightly enough that they can breathe. There's no test at the end. No need to remember every detail. What matters is the quality of attention we bring to the inquiry and the sense of connection, to ideas, to questions, to the strange beauty of existence itself. So take a breath, settle a little deeper, and let's continue this journey into the possibility that reality is far stranger, far more multiple than everyday experience suggests. As we step into the territory of quantum mechanics, let's begin with light, something so familiar, so ordinary, that we rarely think about how deeply strange it actually is. Right now, wherever you are, light is reaching you, maybe from a lamp, maybe from a screen, maybe just the ambient glow of distant streetlights filtering through a window. It feels simple, straightforward. Light travels from a source to your eyes. What could be mysterious about that? Everything, it turns out. For centuries, scientists debated whether light was a wave or a particle. In 1801, Thomas Young conducted his famous double-slit experiment. He shone light through two narrow slits and observed an interference pattern on a screen beyond, alternating bands of light and dark, exactly what you'd expect if light were a wave. Waves from the two slits overlapped, reinforcing in some places, cancelling in others. The case seemed settled. Light is a wave. But then, in the early 20th century, experiments revealed something else. Light also behaves like a stream of particles, tiny packets of energy called photons. When you detect light, you always detect whole photons, never fractions. The photoelectric effect, explained by Einstein in 1905, only makes sense if light comes in discrete chunks, not continuous waves. So which is it, wave or particle? The answer quantum mechanics offers is both, and neither. Light is something more fundamental, something that can exhibit wave-like or particle-like properties depending on how we observe it. It's not that we're ignorant of its true nature, it's that it doesn't have a single true nature. Its nature is contextual, observer-dependent, irreducibly strange. Here's where it gets truly extraordinary. In the 1920s, physicists refined the double-slit experiment, this time sending photons through one at a time. You might expect each photon to go through one slit or the other, behaving like a little particle, and gradually build up two bright bands on the screen, one behind each slit. But that's not what happens. Even when sent individually, with long pauses between them, the photons still create an interference pattern. Each single photon somehow knows about both slits, as if it passes through both simultaneously and interferes with itself. But if you try to determine which slit the photon actually goes through, by placing a detector at each slit, the interference pattern disappears. Suddenly the photon behaves like a particle again, going through one slit or the other, creating two simple bands on the screen. The act of observation changes the outcome, not because we disturb the photon mechanically, but because observation itself forces reality to choose between possibilities that were previously existing simultaneously. This isn't a flaw in our instruments or our understanding. It's how reality actually works at the quantum level. The universe doesn't commit to definite states until something asks it to, and from this verified strangeness, a question naturally emerges. If observation forces one outcome into being, what happens to all the other possibilities that were equally real just a moment before? From the strange behavior of light, we turn to perhaps the most famous thought experiment in all of quantum mechanics, one that has, unfortunately, been misunderstood nearly as often as it's been cited. In 1935, Austrian physicist Erwin Schrödinger proposed an imaginary scenario designed not to explain quantum mechanics, but to highlight how absurd it seemed when extended beyond the microscopic realm. He asked us to picture a cat sealed in a box with a device containing a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter detects it, triggering a mechanism that breaks the vial, releasing poison that kills the cat. If the atom doesn't decay, the cat lives, Here's the quantum strangeness. Before we open the box, the radioactive atom exists in a superposition of states, both decayed and not decayed simultaneously. According to the standard interpretation of quantum mechanics, this superposition extends to everything connected to the atom. The device is in a superposition of triggered and not triggered. The vial is both broken and intact, and the cat, impossibly, absurdly, is both alive and dead. Only when we open the box and observe the system does reality collapse into one outcome or the other. Schrödinger intended this as a criticism, a way of showing that quantum mechanics, if taken literally, leads to ridiculous conclusions. A cat can't actually be both alive and dead, can it? But let's set aside the morbid imagery for a moment and focus on what the thought experiment reveals. It's pointing toward a genuine mystery. Where is the boundary between the quantum realm, where superposition is real, and the classical realm, where things are definitively one way or another? Atoms exist in superposition. That's confirmed beyond doubt. But atoms make up molecules. Molecules make up cells. Cells make up cats. At what point does the fuzzy maybe of quantum mechanics crystallize into the definite yes or no of everyday experience? When does one possibility become the only possibility? Some physicists say the collapse happens when a conscious observer looks. Others say it happens through interaction with the environment, a process called decoherence. Still others, and this is where Everett's many worlds interpretation returns, say it never happens at all. Instead, the superposition persists. The cat is both alive and dead, but in different branches of reality. When you open the box, you don't collapse the wave function, you join one branch or the other. In one world, you open the box and find the cat alive. In another, equally real world, you open it and find the cat dead. Both yous are real, both cats are real, both worlds continue forward forever unaware of each other. This interpretation doesn't require anything to collapse. It doesn't need a special role for consciousness. It simply takes quantum mechanics seriously and follows its mathematics wherever it leads. Whether that's true or not, we can't yet say. But the thought experiment, gently reframed, invites us to sit with the possibility that definiteness might be more local, more subjective than we've ever imagined. That perhaps the universe doesn't choose. Perhaps it allows all outcomes, and what we experience as choice is simply which branch of reality we find ourselves in. It's a humbling thought, and a strangely beautiful one. Let's stay with that moment, the one where possibility becomes actuality. It's called the measurement problem, and it remains one of the most contentious puzzles in physics, unsolved despite a century of brilliant minds wrestling with it. Here's what we know with certainty. Before measurement, quantum systems exist in superposition. After measurement, they don't. Something happens in between, something that transforms multiple simultaneous realities into a single definite outcome. But what is that something? And when, precisely, does it occur? The Copenhagen interpretation, developed in the 1920s primarily by Niels Bohr and Werner Heisenberg, offers one answer. The wave function collapses upon measurement. The act of observation forces nature to commit. But this raises immediate questions. What counts as a measurement? Does it require a conscious observer, or will any interaction do? Is there something special about observation that causes collapse? Or is collapse simply a useful fiction we use to describe what we experience? Some have suggested consciousness plays a crucial role, that the universe remains in superposition until a conscious mind observes it. This idea has a certain appeal, placing awareness at the center of physical reality. But it also raises problems. Did the universe not have definite states before conscious beings evolved? Does the moon cease to exist in a definite position when nobody's looking at it? Others propose decoherence as the answer. As a quantum system interacts with its environment, and everything does, constantly, the delicate superposition gets disrupted, smeared out, effectively collapsed, not by observation but by interaction. This explanation has mathematical rigor behind it, and explains why we don't see quantum effects at large scales, but it doesn't fully solve the problem, because decoherence doesn't actually eliminate the other possibilities from the equations. It just makes them practically unobservable. And then there's Everett's solution, which we keep circling back to. Nothing collapses. The wave function continues evolving exactly as quantum mechanics predicts. All outcomes occur, reality branches, and each branch experiences one definite outcome, giving the appearance of collapse without anything actually collapsing. This interpretation is ontologically extravagant. It multiplies worlds beyond counting, but it's also mathematically clean. It doesn't require adding anything to the equations. It simply takes them at face value. The remarkable thing is that after nearly 100 years, we still don't have consensus. These competing interpretations make identical predictions for every experiment we can currently perform, which means choosing between them isn't a matter of evidence, it's a matter of philosophical preference. Do you favor simplicity of interpretation or simplicity of ontology? Do you trust mathematical elegance or empirical restraint? Perhaps the answer will come from future experiments, new technologies that can probe the boundary between quantum and classical in unprecedented ways. Or perhaps the question will remain forever open, a reminder that science doesn't always converge on single truths. What's certain is this: reality at its most fundamental level refuses to behave the way our intuitions expect. The moment of transition from maybe to definitely, from superposition to singularity, remains wrapped in mystery, and that mystery is the crack through which the possibility of parallel worlds enters the conversation. Not as fantasy, as physics. Now let's meet the man who dared to suggest that the universe never chooses, it simply allows everything. Hugh Everett III was 27 years old when he submitted his doctoral thesis to Princeton in 1957. His advisor was John Wheeler, one of the most creative and open-minded physicists of the era. The thesis was titled The Theory of the Universal Wave Function, and though it was relatively short, just under 100 pages, it proposed something so radical that most physicists either ignored it or dismissed it outright. Everett's central idea was elegantly simple. Take quantum mechanics seriously. Don't add collapse postulates. Don't introduce special roles for observers. Just follow the mathematics wherever it leads. According to the Schrödinger equation, the fundamental equation of quantum mechanics, systems evolve smoothly and deterministically. Superpositions persist. Nothing collapses. But if that's true, why do we experience definite outcomes when we make measurements? Everett's answer: we don't experience definite outcomes. We experience one outcome in one branch of reality, but other versions of us experience different outcomes in other branches. The universe doesn't collapse into one history. It branches into multiple histories, each equally real, each unfolding independently. Every quantum event, every time a particle is measured, every time a photon is absorbed, every atomic decay, every molecular vibration creates a branching point. In some branches, the particle has one spin, in others, another spin. In some branches, the atom decays. In others, it doesn't. The branching is constant, staggeringly prolific, creating an unfathomably complex structure of parallel realities. This solves the measurement problem cleanly. There's no mysterious collapse, no special role for consciousness, no divide between quantum and classical realms. Everything is quantum, everything obeys the same laws. We experience definiteness because we are part of the system, embedded in one branch, with no access to the others. The structure of reality, in Everett's view, resembles an endlessly branching tree, or more accurately, something far more complex than a tree, since the branching occurs continuously, everywhere, at every scale. It's sometimes called the multiverse, though Everett himself preferred the term relative state formulation. The state of any system is always relative to the observer, and observers themselves are branching along with everything else. During his lifetime, Everett's ideas gained little traction. The Copenhagen interpretation dominated, and many physicists found the ontological implications of many worlds too extravagant to accept. Creating infinitely many universes every microsecond seemed wasteful, absurd. Everett left academia, worked on military operations research, and largely abandoned physics. He died in 1982, believing his work had been mostly forgotten. But ideas have a way of persisting. In the decades since, many worlds has gained adherents, particularly among younger physicists and those working on quantum computing, not because it's been proven. No interpretation of quantum mechanics has, but because it's mathematically rigorous, philosophically clean, and makes the same testable predictions as other interpretations, while requiring fewer arbitrary assumptions. Whether Everett was right remains an open question, but his willingness to follow the mathematics into strange territory, to accept implications that seem impossible, rather than patch the equations with arbitrary rules, represents a kind of intellectual courage worth honoring. Reality, it seems, is under no obligation to match our intuitions about economy or simplicity. If we're entertaining the possibility that reality branches, we should pause and ask, what exactly triggers a branch? Does every event create parallel worlds, or only certain kinds of events? This distinction matters. There's a common misconception that many worlds means every decision you make creates branching realities. You choose coffee instead of tea, reality splits. You turn left instead of right, another split. According to this picture, our choices have cosmic consequences, constantly multiplying worlds. But that's not quite right. In Everett's framework, branching occurs at the quantum level, when quantum superpositions interact with other systems in ways that entangle them, creating distinct, non-interfering branches. Classical randomness, by contrast, doesn't create branches. Consider a coin flip. The coin is a macroscopic object, governed by classical physics. Its trajectory is determined by the force of your thumb, air currents, gravitational pull. In principle, if you knew all the initial conditions precisely enough, you could predict the outcome. The appearance of randomness comes from our ignorance, not from quantum indeterminacy. In the many worlds framework, the coin doesn't create new branches. It lands the same way in all branches where the quantum states of relevant particles are identical. But now consider the quantum version, a single atom in a superposition of decayed and not decayed. This is genuine indeterminacy, not merely unknowability. There is no fact about whether the atom has decayed until something interacts with it. When it does interact, reality branches. In one branch, the atom decayed. In another, it didn't. Both outcomes are realized. So the question becomes, which of our choices, if any, are connected to quantum events in such a way that they create branches? Some are, certainly. Your brain is a physical system, and its operation depends on chemical reactions, ion channels, neurotransmitter releases, processes that, at the molecular level, involve quantum effects. It's possible, even likely, that some of your thoughts and decisions have quantum indeterminacy at their root. If that's the case, then yes, your choices might create branches, but not all choices, not all moments. The branching is neither constant at the level of everyday experience, nor entirely absent. It's selective, tied to the specific physical processes that involve genuine quantum uncertainty. This matters philosophically. If every decision branches reality, then in some sense, all versions of your life are being lived. But if only certain quantum events create branches, then the structure of the multiverse is more constrained. Some paths you didn't take truly weren't taken by anyone. They simply didn't happen in any branch. Of course, we don't know the precise boundary. Neuroscience hasn't yet resolved whether macroscopic brain processes depend on quantum effects in crucial ways. Some researchers, like physicist Roger Penrose, have argued that consciousness itself might involve quantum phenomena. Others remain skeptical. What we're left with is a space of uncertainty, fitting perhaps for a theory about multiplicity. The many worlds interpretation doesn't give us a simple formula for what branches and what doesn't. It gives us a framework and invites ongoing investigation. And in that uncertainty, room remains for wonder about which version of your story is unfolding elsewhere, and which remains uniquely yours. Before we leave the quantum realm behind and venture toward cosmological horizons, let's pause to acknowledge something important. The strangeness we've been discussing isn't speculative, it's real. Quantum superposition, entanglement, wave-particle duality, these aren't philosophical musings or theoretical fantasies. They're verified features of nature, confirmed in countless experiments across laboratories worldwide. We've built technologies that depend on them. Quantum mechanics is the most precisely tested theory in the history of science. Consider entanglement. When two particles become entangled through interaction or shared origin, they remain connected in a way that transcends space. Measure the spin of one particle, and you instantly know the spin of the other, even if they're separated by vast distances. Einstein famously called this spooky action at a distance, and he didn't believe it could be real. He thought it revealed a flaw in quantum mechanics. But experiments, particularly those by Alain Aspect in the 1980s, confirmed that entanglement is real. The connection between entangled particles isn't mediated by signals traveling between them. It's instantaneous, non-local, deeply strange, and yet, it's there. We've measured it. We use it in emerging quantum technologies, or consider quantum tunneling. Particles can pass through energy barriers that classical physics says should be impassable. It's as if you rolled a ball toward a hill, and instead of rolling back down if it lacked the energy to reach the top, it simply appeared on the other side. This isn't metaphor. Particles do this. Tunneling is why the sun shines. Nuclear fusion in the sun's core relies on protons tunneling through electromagnetic repulsion barriers. It's why certain chemical reactions occur. It's foundational to the universe's operation. And then there's the double-slit experiment we discussed earlier. It's not just a thought experiment. It's been performed thousands of times with photons, electrons, even large molecules like buckyballs, spheres of 60 carbon atoms. Every time the result is the same. Individual particles behave as though they pass through both slits simultaneously, creating interference patterns that only make sense if each particle exists in multiple states at once. This is the universe we live in, not the clean clockwork universe of Newtonian physics, where everything has a definite position and trajectory. Not even the relativistic universe of Einstein, where space curves and time dilates, but events still unfold in orderly, deterministic ways. We live in a quantum universe, where the boundary between possibility and actuality is blurry, where observation affects reality, where particles remain connected across arbitrary distances. Parallel worlds in this context aren't a departure from established physics. They're an attempt to take established physics seriously. The strangeness is already present, verified in the data. The question isn't whether reality is strange, it's how to interpret that strangeness. And if we accept that particles exist in superposition, that measurements don't simply reveal pre-existing states but bring them into being, that entanglement connects distant systems in causal ways, well then perhaps the idea of branching realities isn't so extravagant after all. Perhaps it's simply the next step in accepting how deeply, irreducibly strange our universe actually is. As we step back from the quantum scale, let's turn our gaze outward, toward the cosmos, toward the vast spaces beyond our planetary home, beyond even our galaxy, toward the farthest reaches of observable space. And then, remarkably, beyond even that, there's a horizon to what we can see, not because our telescopes aren't powerful enough, but because the universe has a finite age. Light has only had about 13.8 billion years to travel since the Big Bang. Anything farther away than light could reach in that time remains beyond our view, not because it doesn't exist, but because its light hasn't arrived yet. This observable universe, the sphere of space from which light has had time to reach us, extends roughly 46 billion light-years in every direction, accounting for cosmic expansion. It contains perhaps 2 trillion galaxies, each with hundreds of billions of stars. It's vast almost beyond comprehension. But here's the question. Does space end at that horizon? Most cosmologists think not. The observable universe is likely just a tiny fraction of the total universe. Space, as far as we can tell, extends far beyond what we can see, possibly infinitely. And if space is infinite, something remarkable follows. An infinite universe containing a finite number of possible configurations must eventually repeat. There are only so many ways to arrange particles in any given volume of space. If you have infinitely many such volumes, eventually every possible arrangement will occur, and not just once, infinitely many times. This is cosmologist Max Tegmark's Level 1 multiverse. It's not speculative in the sense that many worlds is. If space is infinite, and our best measurements of cosmic geometry suggest it might be, then Level 1 follows inevitably. Somewhere out there, beyond the horizon, beyond countless other horizons, there's a region of space identical to ours. Same galaxies, same solar system, same Earth, same you. In fact, there are infinitely many such regions, each containing a version of you reading these words right now. And not only exact copies, there are also regions where things are slightly different, where you chose a different career, or where dinosaurs never went extinct, or where Earth never formed at all. The distances involved are staggering, far beyond anything we could ever reach or observe. Estimates suggest your nearest identical copy is perhaps 10 to the power 1029 meters away. That's a number so large it defies intuition. For comparison, the observable universe is about 10 to 26 meters across. Your nearest twin is incomprehensibly farther. But distance doesn't determine reality. If those regions exist and the mathematics of an infinite universe says they do, then those other yous are just as real as you are. They exist right now, embedded in space continuous with ours, simply too far away for light to ever connect us. This isn't parallel worlds in the sense of separate dimensions. It's parallel worlds in the sense of distant places. Same universe, same 3 dimensions, same physical laws, just unimaginably, unreachably far. It's a humbling thought, and it raises a curious question. If you already have infinite copies scattered across infinite space, does adding quantum branches really make things more extravagant? Or is infinity already so vast that one more flavor of multiplicity barely registers? From the infinity of space, let's turn to the process that might have created that infinity, and in doing so, created far more than just one universe. In 1980, physicist Alan Guth proposed a mechanism called cosmic inflation to explain certain puzzles about the early universe. The idea is that in the first fraction of a second after the Big Bang, space underwent a period of exponential expansion, growing faster than the speed of light, not because anything moved through space faster than light, but because space itself was expanding. Inflation solves several problems in cosmology. It explains why the universe looks roughly the same in all directions, despite regions being too far apart to have ever been in contact. It explains the large-scale structure of the cosmos, and it explains why space appears geometrically flat. The theory has been remarkably successful, supported by observations of the cosmic microwave background radiation, but inflation, it turns out, has an unexpected consequence. Once it starts, it's hard to stop. Everywhere at once, anyway. Physicist Andre Linde developed this idea into what's called eternal inflation. Here's how it works. Inflation is driven by a quantum field called the inflation field. In most regions of space, this field eventually settles into a low-energy state, and inflation ends. The universe transitions into the more sedate expansion we observe today. But quantum mechanics introduces randomness into this process. In some regions, quantum fluctuations cause the inflation field to jump back to a high-energy state, and inflation continues. Those regions keep inflating, expanding exponentially, and within them, the same process repeats. Some subregions stop inflating and form bubble universes, calm pockets where galaxies and stars can form, but other subregions continue inflating, spawning their own bubbles in an endless self-perpetuating process. The result is eternal inflation. Once inflation starts, it never stops completely. It continues forever in some parts of the broader structure, constantly creating new bubble universes. Each bubble is causally disconnected from the others, separated by regions of space that are still inflating, growing so fast that no signal can cross from one bubble to another. Our universe, in this picture, is just one bubble in an infinite foam. And here's the truly remarkable part. The physical constants in each bubble might be different. The strength of gravity, the mass of electrons, the speed of light, these could vary from bubble to bubble, determined by how the quantum field settled when inflation ended in each region. Most bubbles might be sterile, devoid of structure. Perhaps gravity is too strong, causing everything to collapse immediately, or too weak, preventing galaxies from forming. Perhaps atoms can't hold together, or stars can't ignite. The conditions necessary for life might be extraordinarily rare, but if eternal inflation is real, there are infinitely many bubbles, and in an infinity of variations, even extraordinarily rare conditions will occur infinitely many times. Somewhere in another bubble, there might be a universe almost like ours, but with slightly different physical laws. Stars burn hotter, time flows differently, matter organizes in unfamiliar ways, and in yet another bubble, something utterly alien, structures and processes we lack even the concepts to imagine. This isn't quantum branching, it's cosmic budding, new universes constantly born from the quantum froth of eternal inflation, each a separate world with its own laws, its own history, its own fundamental nature, and all of it perhaps happening right now in a larger structure we can never observe. Now we return to Hugh Everett's many worlds, but with a slightly different lens. Max Tegmark classified this as the level 3 multiverse. distinct from the infinite space of level 1 and the bubble universes of level 2, yet related in fascinating ways. Level 3 is the quantum multiverse, the structure of branching realities created by quantum measurements. Every time a quantum system is observed, reality splits. Electrons go left and right, atoms decay and don't decay, photons pass through one slit and both slits. Each outcome occurs, but in different branches. This branching is constant, occurring everywhere, all the time. Every particle interaction involves quantum processes, and each such interaction is a potential branching point. The number of branches is staggering, growing exponentially with every passing moment. After just 1 second, the structure has branched more times than there are atoms in the observable universe. What does this branching structure look like? We're tempted to imagine it as a tree, one trunk splitting into 2 branches, each splitting again, and so forth. But that's too simplistic. The branching is happening simultaneously everywhere, at every scale, in overlapping, interfering ways. It's less like a tree, and more like an incomprehensibly complex foam, or perhaps something beyond geometric metaphor entirely. The branches are often called worlds, but they're not separate universes in the sense of different spaces. They're more like different threads of history, all embedded in the same underlying quantum state, what Everett called the universal wave function. Each branch evolves according to the same physical laws. Each is equally real, but they're effectively isolated from one another by a process called decoherence, which prevents interactions between branches. Here's something curious. Tegmark has shown mathematically that level 3 doesn't actually add anything to the ensemble of possibilities already present in level 1. If space is infinite and all possible configurations occur somewhere, then everything that happens in the quantum branching of level 3 also happens somewhere in the infinite space of level 1. They're different ways of organizing the same multiplicity, but subjectively, they feel different. In level 1, your copies are distant in space. In level 3, they're near in some abstract sense, split off from you microseconds ago, living through slightly different versions of the same moment. This raises philosophical questions about identity. If you split into 2 branches, are both of you still you? They share your history up to the branching point. They have your memories, your personality, your intentions. But from the moment of branching, their experiences diverge. One version sees the electron spin up, the other sees it spin down. In that moment, do you become 2 people, or does one you continue in one branch while something else continues in the other? There's no consensus answer. Some philosophers argue that personal identity is preserved across branches. Both versions are you. Others argue that branching creates distinct individuals who happen to share a common past. Still others question whether the question even makes sense, given that no branch can ever know what happens in the others. What we're left with is a picture of reality where every quantum possibility is realized, where the universe doesn't choose, where history is not a single thread but a vast, ever-branching tapestry of actualized potentials. Whether this is comforting or dizzying depends, perhaps, on how you hold it. Let's shift our attention to yet another framework, one that emerges from string theory and suggests that our entire universe might be just one surface floating in a higher dimensional space. String theory is an attempt to reconcile quantum mechanics with general relativity, to find a unified description of all fundamental forces. The core idea is that the basic constituents of reality aren't point-like particles but tiny vibrating strings. Different vibration patterns correspond to different particles, electrons, quarks, photons, and so on. But string theory comes with a peculiar requirement. It only works mathematically if space has more than the 3 dimensions we experience. Depending on the version, it requires 9, 10, or even 11 spatial dimensions. Where are these extra dimensions? Why don't we perceive them? The standard answer is that they're compactified, curled up so small that we can't detect them directly. Imagine an ant walking on a tightrope. From a distance, the rope looks one-dimensional, but up close it has thickness. It's actually a 2-dimensional surface wrapped into a very thin cylinder. Similarly, our 3-dimensional space might be embedded in a higher dimensional manifold, with the extra dimensions too small to perceive. But there's another possibility, suggested by brain cosmology. In this picture, our universe is a 3-dimensional brain, short for membrane, floating in a higher dimensional space called the bulk. The particles and forces we experience are confined to our brain. Gravity, however, can propagate through the bulk, which is why it's so much weaker than other forces. Now here's the speculative leap. If our universe is a brain in a higher dimensional space, might there be other brains nearby, other three-dimensional surfaces, perhaps just a millimeter away in the higher dimensions, but completely inaccessible to us because we're trapped on our brain? This idea, developed in the early 2000s by physicists like Lisa Randall and Raman Sundram, suggests a kind of parallel universe, different from anything we've discussed so far, not distant in space like Level 1, not separated by quantum branching like Level 3, not disconnected by eternal inflation like Level 2, instead, separated by dimensions, existing right alongside us, yet utterly unreachable because the directions to get there aren't available within our three-dimensional space. What might these other brains be like? If they're governed by the same underlying physics, they might have similar laws, similar particles, similar structures, but they could also be vastly different. The way extra dimensions are compactified on another brain might lead to different forces, different particles, different possibilities for complexity. Some cosmologists have even speculated that the Big Bang might have been the result of a collision between brains, two membranes brushing against each other in the higher dimensional bulk, releasing enormous energy that manifested as the explosive beginning of our observable universe. This is admittedly highly speculative. We have no direct evidence for extra dimensions, let alone for other brains. But the mathematics of string theory and brain cosmology are rigorous, and they solve certain problems in theoretical physics. Whether they describe reality or are merely beautiful mathematical structures remains an open question. Still, it's worth considering the image, an infinite space, full of three-dimensional surfaces like ours, floating alongside one another, separated not by distance, but by directions we cannot move in, dimensions we cannot perceive. It's a strange and humbling picture, and yet another way reality might be far more multiple than everyday experience suggests. Now we arrive at perhaps the most radical proposal of all, one that doesn't start with physics but with mathematics, and ends with a multiverse so vast it includes every logically possible reality. Max Tegmark, the same physicist who classified multiverse types into levels, proposed what he calls the Level 4 multiverse, or the mathematical universe hypothesis. The idea is both simple and staggering. Every mathematical structure that exists abstractly also exists physically as a universe. Let's unpack that. Physics describes the universe using mathematics, equations, geometries, numbers. These aren't just tools we use to model reality. According to Tegmark, they are reality. The physical universe is a mathematical structure. Particles are points in an abstract space. Forces are symmetries. Time is a dimension. Everything we observe is, at the deepest level, mathematical. But if our universe is a mathematical structure, why should it be the only one? Mathematics contains infinitely many structures, different geometries, different symmetries, different equations. Why should only one be instantiated as a physical reality? Tegmark's answer: they all are. Every mathematical structure that's logically consistent exists as a universe where space has 4 dimensions, a universe where time flows backward, a universe where particles interact according to entirely different force laws, a universe where the structure is so alien that nothing we'd recognize as matter or energy or space could form. This is Level 4, the ensemble of all mathematical structures. It's not just a multiverse, it's the ultimate multiverse, encompassing everything that can possibly exist in any logical sense. At first glance, this seems absurdly extravagant, but Tegmark argues it's actually the simplest possibility. If you accept that our universe is mathematical, you have to answer why this particular mathematical structure and not others. Any answer you give requires additional assumptions because of some meta-law, or because of some selection principle, or because God chose it. But these explanations are more complex than simply saying all mathematical structures exist. No selection needed, no special explanation, just the pure fact of mathematical existence, translating into physical existence. Of course, most of these universes would be unimaginably strange. Many wouldn't support complexity, life, or consciousness. They'd be simple, sterile, governed by laws too rigid or too chaotic for interesting structures to form. But in an ensemble that includes literally every possibility, some universes will have the right conditions, and we, necessarily, find ourselves in one of them, because only in such universes can beings capable of asking these questions exist. This connects to the anthropic principle, which we'll explore more later, but for now, just hold the strangeness of the idea. If Tegmark is right, reality isn't just multiple, it's omni-multiple. Every coherent possibility is actual, every logically consistent dream is being dreamed, and the universe we inhabit, with its particular particles, particular forces, particular constants, is just one point in an infinite mathematical landscape. Is it true? We have no way to test it, no way to confirm or refute it empirically. It's more philosophy than physics, though rooted in serious mathematical considerations. But as a thought experiment, it stretches our imagination to the breaking point. It invites us to consider that existence itself might have no boundaries except logical consistency, and in that vastness perhaps there's a certain awe. So here we are, having surveyed a landscape of possibilities, infinite space containing infinite copies of us, eternal inflation spawning endless bubble universes, quantum branching creating moment-by-moment multiplicities, higher dimensional brains floating alongside ours, mathematical structures manifesting as physical realities. Each framework offers a different vision of multiplicity, a different way reality might exceed the boundaries of the observable, and none of them is proven. That's worth sitting with for a moment. We have strong evidence for some of the foundations. Cosmic inflation is well supported. Quantum mechanics is verified beyond reasonable doubt. The mathematics of string theory and multiverses is rigorous, but the leap from those foundations to the full-fledged multiverse proposals remains speculative. We don't know which, if any, of these frameworks is correct. Different physicists favor different interpretations based on which principles they prioritize. Some value mathematical elegance and favor Everett's many worlds because it doesn't require adding collapse mechanisms to quantum theory. Others value empirical restraint and prefer interpretations that stick closer to what can be measured. Some are drawn to the grandeur of eternal inflation. Others find it ontologically excessive. This pluralism is worth celebrating. It reflects the fact that science at the frontiers isn't a march towards certainty, it's an exploration of possibilities. These multiverse ideas aren't competing in the way theories usually do, because most of them aren't mutually exclusive. Level I, Level 2, and Level 3 could all be true simultaneously. Brain cosmology could be compatible with quantum branching. The mathematical universe hypothesis, if true, would encompass all the others. What we're engaging with here isn't a settled body of knowledge. It's a conversation, an ongoing inquiry into the nature of existence. And that conversation is enriched by the variety of perspectives, the willingness of different thinkers to follow different threads of logic and see where they lead. For us, as listeners in the quiet of the night, the multiplicity of frameworks mirrors the multiplicity they describe. Just as there might be many worlds, there are many stories about many worlds. We don't have to choose one as the truth and discard the others. We can hold them lightly, appreciate the insights each offers, and remain open to the possibility that reality is larger and stranger than any single framework captures. This isn't intellectual weakness, it's intellectual humility. The universe is under no obligation to conform to our preferences for simplicity or elegance or empirical accessibility. It simply is what it is. And our task isn't to force it into a box, but to listen carefully to what it's telling us, through mathematics, through experiments, through the quiet consistency of natural law. Perhaps parallel worlds exist. Perhaps they don't. Perhaps the question itself will remain forever unanswerable. But the act of asking, the willingness to follow these ideas wherever they lead, the openness to vastness and strangeness, that has value regardless of where we end up. And so we continue, not toward certainty, but toward understanding, not to solve the mystery, but to deepen our relationship with it. As we turn from theoretical frameworks toward something more tangible, let's consider an unusual observation, a peculiar anomaly in the most distant light we can detect, and what it might, just possibly, suggest about reality beyond our cosmic horizon. In the aftermath of the Big Bang, the universe was filled with a hot, dense plasma. About 380,000 years later, it cooled enough for atoms to form, and light could finally travel freely through space. That ancient light, stretched by cosmic expansion into microwave wavelengths, still fills the universe today. We call it the cosmic microwave background radiation, or CMB. The CMB is remarkably uniform, with a temperature of about 2.7 Kelvin in every direction we look. But not perfectly uniform. There are tiny fluctuations, variations of about 1 part in 100,000, corresponding to slightly denser regions in the early universe, regions that would eventually collapse under gravity to form galaxies, clusters, and the cosmic web of structure we observe today. NASA's Wilkinson Microwave Anisotropy Probe, WAP, mapped these fluctuations in unprecedented detail, starting in 2001. And in those maps, astronomers found something unexpected, a region of sky about 5 degrees across, where the temperature is slightly colder than it should be, not by much, just a fraction of a millikelvin cooler than the surrounding regions. But statistically, a cold spot that large and that cold is unusual. It shouldn't be there, or at least, it shouldn't be there with the intensity observed. This became known as the CMB cold spot. Various explanations have been proposed. Perhaps it's just a statistical fluke, unlikely but possible. Perhaps it corresponds to a supervoid, an unusually empty region of space between us and the CMB, which would affect the light passing through in ways that could create a cold spot. Or perhaps, and this is where speculation enters, it's evidence of something more extraordinary. In 2007, physicists Laura Mersini-Houghton and Richard Holman suggested that the cold spot might be a bruise left by a collision between our universe and another universe in the early moments of cosmic inflation. If our bubble universe brushed against another bubble, the interaction could have left a signature, a region where the energy distribution was slightly altered, manifesting now as a temperature anomaly in the CMB. This is, to be clear, a speculative interpretation. Most cosmologists favor more prosaic explanations. The supervoid hypothesis has gained support from subsequent observations. But the multiverse collision idea remains a possibility, however remote. It represents the kind of evidence we might expect if eternal inflation is real and bubble universes occasionally interact. Other potential signatures have been proposed as well. Patterns of concentric circles in the CMB, which some have interpreted as gravitational wave echoes from collisions in a cyclic cosmology. Anomalous alignments of temperature fluctuations that don't match the standard inflationary model's predictions. Each of these observations has alternative explanations, and none constitutes definitive proof, but they remind us that evidence, if it exists, might be subtle, not a glowing portal to another dimension, not a clear signal spelling out parallel worlds exist. Instead, faint traces in ancient light, statistical anomalies that require careful interpretation, echoes of processes occurring in the first fraction of a second after the Big Bang. The universe is whispering. Whether it's telling us about other universes or simply about aspects of our own we don't yet understand, remains an open question. From cosmic anomalies, let's turn to a different kind of evidence, one based not on unusual observations, but on the remarkable ordinariness of the physical constants that govern our universe. Consider the strength of gravity. It's extraordinarily weak compared to other forces. The electromagnetic force, for instance, is about 1036 times stronger. A tiny magnet can lift a paperclip despite the entire Earth's gravitational pull working against it. But if gravity were just slightly stronger, stars would burn through their fuel much faster, leaving insufficient time for life to evolve. If it were slightly weaker, stars might never ignite at all, leaving the universe dark and cold. Or consider the strong nuclear force which holds atomic nuclei together. If it were slightly weaker, only hydrogen would be stable. No complex chemistry, no carbon, no life. If it were slightly stronger, hydrogen would be rare, and different fusion processes would dominate, likely making the universe inhospitable. Or the cosmological constant, which governs the expansion rate of the universe. Theoretical calculations suggest it should be vastly larger than it is. If it were, space would expand so rapidly that galaxies, stars, and planets could never form. Matter would be flung apart faster than gravity could pull it together. These are just a few examples. There are dozens of physical constants, masses of particles, strengths of forces, ratios of fundamental quantities that appear precisely calibrated to allow for complexity, structure, and eventually life. Change any of them by more than a small percentage, and the universe becomes sterile. This is called cosmological fine-tuning. It's not controversial that it exists. What's controversial is what it means. One explanation is design. An intelligence deliberately set the constants to permit life. But this raises more questions than it answers. Who or what is this intelligence? And where did it come from? Another explanation is necessity. Perhaps the constants couldn't be otherwise. Maybe there's a deeper theory, yet to be discovered, that uniquely determines their values. But so far, no such theory exists, and current physics suggests the constants could, in principle, have a wide range of values. A third explanation is luck. Maybe we just got incredibly fortunate. Out of all the possible universes that could have existed, ours happens to be one of the rare ones where conditions allow complexity, but this explanation feels deeply unsatisfying. The odds are so staggeringly small that calling it luck seems inadequate. And then there's the multiverse explanation. If there are countless universes, each with different physical constants, as eternal inflation suggests, then the fine-tuning isn't mysterious at all. Most universes are sterile, but in the rare ones where constants fall within the narrow range that permits life, observers eventually arise, and those observers will inevitably find themselves in a fine-tuned universe, because they couldn't exist otherwise. This is the anthropic principle. We observe what we observe because we're here to observe it. It's a selection effect, not evidence of design or luck or necessity, but simply a consequence of the fact that only certain kinds of universes can be observed from within. The anthropic explanation only works, of course, if the multiverse exists. If there's only one universe, it doesn't solve the problem, it just restates it. But if level 1 or level 2 or level 4 multiverses are real, fine-tuning ceases to be puzzling. It becomes expected. This doesn't constitute proof, but it's a kind of evidence, indirect, philosophical, based on reasoning about probabilities and possibilities. If the multiverse makes something that would otherwise be inexplicably unlikely into something inevitable, that's an argument in its favor, even if it's not the kind of evidence we can point telescopes at. And so the constants whisper too, in their way, about vastness beyond the visible. Let's shift now to something tangible, something we can build in laboratories, and consider what it might be telling us about the nature of computation, and perhaps about the structure of reality itself. Quantum computers are devices that harness quantum superposition to perform calculations. Unlike classical computers, which process information in bits that are either 0 or 1, quantum computers use qubits that can be 0, 1, or both simultaneously. When you have many qubits in superposition, the system explores an enormous number of possibilities at once. 10 qubits can represent 1024 states simultaneously. 50 qubits, over a quadrillion states. 300 qubits, more states than there are atoms in the observable universe. This parallelism gives quantum computers extraordinary potential power for certain problems, factoring large numbers, simulating quantum systems, optimizing complex networks. In 2019, Google announced it had achieved quantum supremacy, demonstrating that their quantum processor performed a specific calculation far faster than any classical computer could. But here's the curious question. Where is the computation happening? Physicist David Deutsch, one of the pioneers of quantum computing, has argued that the computational power of quantum computers can't be explained by processes occurring in our branch of the universe alone. When a quantum computer with 300 qubits performs a calculation, it's manipulating more states than there are particles in the observable universe. Where is the physical substrate that's doing all this processing? Deutsch's answer, rooted in his adherence to the many worlds interpretation, is that the computation is distributed across parallel branches. Each branch handles part of the calculation. The qubits exist in superposition, meaning they're spread across many worlds, and the computation happens simultaneously in all of them. When the calculation completes and you measure the result, you're seeing the outcome of a massive parallel process that unfolded across the multiverse. If this is correct, quantum computers are, in a sense, reaching into other branches of reality and borrowing their computational resources. They're multiverse explorers, not in the sense of sending signals to other worlds, but in the sense of utilizing the quantum structure that connects all branches. Not everyone agrees with this interpretation, of course. Some researchers argue that decoherence and the mathematics of quantum information theory are sufficient to explain quantum computing without invoking parallel worlds. The computation, they say, happens in the entanglement structure, the correlations between quantum states which exist in a single universe. But Deutsch's perspective offers a compelling response to the question of where the computation physically occurs. It's not hand-waving or mysticism, it's a straightforward consequence of taking many worlds seriously. If branches are real, and qubits are genuinely in superposition across those branches, then the computational work is being done in those branches. This doesn't prove many worlds is true, but it provides a concrete example of how the interpretation makes sense of something otherwise puzzling. And as quantum computers become more powerful, capable of performing tasks that classical computers couldn't accomplish in the lifetime of the universe, the question of where all that processing is happening becomes more pressing. Perhaps we're not just theorizing about parallel worlds. Perhaps we're already interacting with them, using them as tools, exploiting their reality to solve problems in our branch. The quantum computer humming in a lab, cooled to near absolute zero, its qubits suspended in superposition, it might be the closest thing we have to a window into the multiverse. Or perhaps it's just extraordinarily clever physics, fully explainable within a single universe. Either way, it's a reminder that the abstract ideas we've been exploring have concrete implications, touch real technologies, connect to questions we can investigate empirically. The boundary between theory and reality is less sharp than we might think. Having explored potential signs of parallel worlds, we should pause and confront something directly. Most of what we've discussed is untestable, at least with current technology, and some of it might be untestable in principle. This creates a philosophical problem. Science is generally understood to proceed through falsifiability, the idea, articulated by philosopher Karl Popper, that a theory is scientific only if it makes predictions that could, at least in principle, be proven wrong by observation or experiment. If a theory is compatible with every possible outcome, if no conceivable evidence could refute it, then it's not really a scientific theory at all. It's metaphysics. Many critics of multiverse theories argue they fall into this category. How do you test the claim that there are infinite universes beyond our cosmic horizon? By definition, they're beyond observation. How do you confirm that quantum branching creates parallel worlds, if those worlds are forever isolated from ours by decoherence? How do you verify the mathematical universe hypothesis, which posits realities so different from ours that we can't even formulate experiments relevant to them? These are fair objections, and they've led to vigorous debate within the physics community. Some physicists, particularly those in older generations, view multiverse theories with suspicion, seeing them as a departure from the empirical rigor that made physics successful. Others, often younger theorists, argue that traditional falsifiability is too restrictive and doesn't account for how modern cosmology and quantum mechanics work. The counterargument goes something like this. Multiverse theories aren't proposed arbitrarily. They emerge naturally from well-tested theories like cosmic inflation and quantum mechanics. We don't observe parallel worlds directly, but we do observe the phenomena that suggest them. Inflation explains the structure of the CMB. Quantum mechanics predicts superposition and entanglement, which we verify constantly. Multiverses are implications of those verified theories, not free-floating speculations. Moreover, some aspects of multiverse theories might be testable indirectly. If eternal inflation is correct, we might find signatures in the CMB, patterns, correlations, anomalies that wouldn't exist otherwise. If quantum branching is real, we might be able to perform increasingly sophisticated quantum experiments that distinguish between interpretations. The fact that we haven't definitively tested these ideas yet doesn't mean they're untestable forever. Still, the honest answer is that we might never know for certain. Some versions of the multiverse, particularly Level 1 and Level 2, involve regions of space causally disconnected from ours. No signal can ever reach us from beyond the cosmic horizon or from another bubble universe. The evidence, if it exists at all, is indirect. Mathematical consistency, explanatory power, philosophical elegance. Is that enough? Different people will answer differently. Some find the mathematical beauty and conceptual coherence of multiverse theories compelling, even in the absence of direct empirical confirmation. Others remain skeptical, preferring to withhold judgment until more concrete evidence emerges. What's important is acknowledging the uncertainty. These ideas are at the frontier of human knowledge, where science blends with philosophy, where the questions we can ask exceed the answers we can currently provide. That doesn't make them invalid. But it does mean we should hold them with appropriate humility, recognizing that we're speculating, exploring, wondering, not asserting certainties. The absence of evidence isn't evidence of absence, but neither is it evidence of presence. It's simply absence, a space where possibilities live, neither confirmed nor refuted, waiting quietly for whatever insights future discoveries might bring. Despite the challenges, the search continues. Scientists around the world are devising ever more creative ways to probe the boundaries of the knowable, to look for traces of the multiverse in the subtle patterns of observable reality. Some searches focus on the cosmic microwave background. As we discussed, anomalies like the cold spot might be evidence of bubble collisions. Researchers are developing increasingly sophisticated statistical methods to analyze CMB data, looking for patterns that don't match the standard cosmological model. Even if the signals are subtle, the data is exquisitely detailed. The Planck satellite, which mapped the CMB from 2009 to 2013, provided measurements precise enough to test many inflationary models. Future missions might offer even greater sensitivity. Others focus on gravitational waves. Since 2015, detectors like LIGO have been observing ripples in space-time caused by colliding black holes and neutron stars. Gravitational waves carry information about the early universe in ways that electromagnetic radiation doesn't. Some theorists have proposed that certain patterns in the gravitational wave background, ripples left over from cosmic inflation, might bear signatures of bubble collisions or other multiverse phenomena. Still others explore particle physics. The Large Hadron Collider, which famously discovered the Higgs boson in 2012, probes the highest energies accessible to current technology. While it hasn't found evidence for parallel worlds, it's searching for hints of extra dimensions, supersymmetry, and other features predicted by theories like string theory. If found, these wouldn't prove the multiverse directly, but they'd lend support to the frameworks that predict it. And then there are quantum experiments. Physicists are designing tests to probe the boundary between quantum and classical behavior, to explore decoherence with ever greater precision, to search for anomalies that might distinguish between interpretations of quantum mechanics. Some have proposed experiments with increasingly large quantum systems, viruses, even tiny diamonds, to see if superposition persists at larger scales. If many worlds is correct, these systems should branch just like particles do, though the branches would immediately decohere. None of these searches have yielded definitive evidence yet, but that doesn't diminish their value. Science progresses as much through ruling out possibilities as through confirming them. Each null result narrows the space of viable theories, refines our models, pushes us toward deeper understanding, and there's something beautiful in the act of searching itself. Humanity, from its small planet orbiting an ordinary star, using instruments cobbled together from the periodic table, attempting to discern whether reality extends beyond the visible. It's audacious, perhaps even absurd, but it's also deeply characteristically human. We don't know if we'll ever find conclusive evidence for parallel worlds. Perhaps the multiverse is real but forever beyond empirical reach. Perhaps it's a beautiful idea that doesn't correspond to physical reality. Or perhaps decades or centuries from now, some clever experiment or observation will reveal something unmistakable, a signal, a pattern, a window into vastness we can currently only imagine. Until then, we search, we wonder, we devise new questions, build new instruments, refine new theories, not because we're guaranteed answers, but because the questions themselves matter, because the act of pushing against the boundaries of knowledge, regardless of what we find there, is part of what makes us who we are. And in that searching, perhaps, there's already a kind of fulfillment. Now let's bring this vast cosmic speculation back to something intimate, to you, and the paths your life might have taken but didn't. Think of a significant choice you made years ago. Perhaps you accepted a job offer in a new city, leaving behind friends and familiar places, or perhaps you declined it, staying where you were. Maybe you ended a relationship, or began one. Maybe you pursued a particular field of study, closing doors to others. Every life is built from such moments, branching points where one decision led forward and countless alternatives faded into the realm of what might have been. We carry these unlived lives with us, don't we? They haunt us gently. We wonder, sometimes late at night, what would have happened? Who would we have become? Would we be happier, more fulfilled, more ourselves? Or would we have encountered different challenges, different regrets, and found ourselves wondering about the path we actually took? In the ordinary understanding of reality, these alternative paths are purely hypothetical. They exist only in imagination, as thought experiments we use to make sense of our choices and their consequences. The decision was made, the path was chosen, the other possibilities dissolved into mere abstractions, but if the many worlds interpretation is correct, that understanding is wrong. Those other paths didn't dissolve. They unfolded. Somewhere, not in another location, but in another branch of the quantum multiverse, a version of you made the opposite choice, accepted the job you declined, stayed when you left, spoke when you remained silent, and from that moment, their life diverged from yours. Different experiences, different relationships, different challenges, a different story, but one rooted in the same origin, and not just one alternative. If branching occurs at the quantum level constantly, then there are countless versions of you, some nearly identical, differing only in the minutest quantum fluctuations that had no macroscopic consequences, and some radically different, shaped by quantum events that happen to influence crucial neurons in moments of decision. How does this make you feel? For some, it's comforting. The weight of regret softens when you realize that, in some sense, you did take that other path. Every possibility was realized somewhere. Nothing was truly lost. The life you didn't live is being lived. For others, it's dizzying. If every choice branches reality, does that diminish the significance of our choices? If all outcomes occur, does it matter which one we experience? Both responses are valid. There's no single correct way to feel about living in a branching universe, if indeed we do. What's interesting is how the possibility reframes our relationship to choice, to paths taken and not taken, to the narratives we construct about who we are and who we might have been. Perhaps you've made peace with your choices. Perhaps you carry regrets. Perhaps you're still wondering, still imagining, still playing out alternative scenarios in the theatre of your mind. The many worlds interpretation doesn't resolve those feelings, but it does offer a different lens through which to view them, one where possibility isn't extinguished by actuality, where the roads not taken continue winding forward, walked by echoes of ourselves in realities just beyond perception. And in that vastness, perhaps, there's a kind of gentle permission to be at peace with the life you're actually living. From that thought, a harder question emerges, one that strikes at the heart of how we understand agency and meaning. If all possible outcomes occur in some branch of the multiverse, do our choices actually matter? If you can't avoid making every decision because in some branches you choose A and in others you choose B, then what does it mean to say that you're choosing at all? This is sometimes called the many worlds moral hazard. The worry is that if everything happens somewhere, then nothing you do has real consequences. Want to make the responsible choice? It happens in some branches. Want to make the reckless one? That happens too. You're not steering your life so much as existing across all possible steerings simultaneously. On the surface, this seems to undermine the very notion of choice. But let's look more carefully. First, even in a branching universe, you still experience one particular sequence of events. Your subjective experience follows a single thread through the branching structure. You can't perceive the other branches, can't access their outcomes, can't live all lives simultaneously. From the inside, your experience is singular, coherent, definite. So even if other versions of you make different choices, this version, the one you identify with, the one reading these words right now, still faces genuine decisions with real consequences for the life you'll continue to experience. The fact that another you experiences different consequences doesn't make your consequences any less real for you. Second, branching in many worlds doesn't mean all outcomes are equally probable. Quantum mechanics assigns amplitudes to different branches, which translate into probabilities. Some outcomes are vastly more likely than others. When you make a choice, you're not creating an egalitarian democracy of possibilities. You're steering towards certain branches and away from others, even if the steering isn't absolute. Third, and perhaps most importantly, the meaning of a choice doesn't come solely from its uniqueness. What makes a choice significant isn't that only one outcome occurs in the entire cosmos. It's that the outcome matters to you, shapes your experience, affects the people around you in this branch. Consider love. If I tell someone I love them, The significance of that statement doesn't depend on whether I'm the only version of me in all of reality who says it. The significance comes from the intention, the vulnerability, the connection it creates in this relationship, in this moment, in this thread of experience, or consider art. If a painter creates a masterpiece, does it lose value if somewhere in another branch, a version of them created something different? Of course not. The painting exists here, moves people here, contributes beauty to this world. The same principle applies to moral choices. If you act with kindness, if you help someone in need, the good you do is real and local. It matters to the person you helped, in this branch, regardless of what other versions of you might be doing elsewhere. So perhaps the question isn't whether choices matter, but how they matter. In a singular universe, choices determine the only future that will unfold. In a branching universe, choices determine which future you'll experience. The ontological status shifts, but the practical and moral significance remains. You are still responsible for the life you live, the impacts you create, the person you become. Parallel selves in other branches don't diminish that. If anything, they emphasize it. This branch, this life, these choices are yours in a way nothing else is, and that still matters profoundly. But who, exactly, are these parallel versions of you? And in what sense, if any, are they you? This is where parallel worlds intersect with deep questions in the philosophy of personal identity, questions that have occupied thinkers for centuries, long before quantum mechanics entered the picture. Traditionally, philosophers have asked, what makes you the same person over time? You've changed enormously since childhood. Your cells have been replaced, your memories have evolved, your beliefs and personality have shifted. In what sense is the person you are now the same person you were 20 years ago? Various answers have been proposed. Some say identity is rooted in physical continuity, the same body, the same brain, or at least a continuous chain of causation connecting past and present. Others say it's psychological continuity, the same memories, personality traits, sense of self. Still others, like philosopher Derek Parfit, have argued that personal identity isn't what matters. What matters is psychological connectedness, the web of memories, intentions, and traits that link one moment to the next. Now add parallel worlds to this puzzle. Suppose you and your parallel self share identical histories up to a certain branching point. From that moment, your experiences diverge. Same origin, same memories up to the branch, but different futures unfolding. Are you the same person, or are you two distinct people who happen to share a common past? One way to think about it is that personal identity isn't binary. It comes in degrees. Your parallel self, split off a microsecond ago, is almost entirely you. Same thoughts, same memories, barely distinguishable. But a parallel self that branched off decades ago, who made different life choices and had different experiences, might be much less you in any meaningful sense. Same genetic starting point, but shaped by different influences into someone potentially quite different. Parfit's philosophy is particularly relevant here. He argued that we shouldn't think of personal identity as an all-or-nothing matter of a single self persisting over time. Instead, there are degrees of psychological connectedness and continuity. A version of you from a parallel branch is connected to you. You share a common history, but the connectedness weakens as the branches diverge. This has implications for how we think about those parallel selves. If a parallel you exists in a branch that split off yesterday, making nearly identical choices, they're very close to you in Parfit's sense. If a parallel you exists in a branch that diverged in your childhood, leading to a completely different life, they're more like a sibling, related but distinct. And here's a curious thought. Even in a single universe without quantum branching, your past self is in some ways like a parallel self. The you of 20 years ago made choices that shaped the present you, but you can't go back and consult them, can't share their experiences directly, can't merge your current knowledge with their perspective. They're continuous with you, but also separate, existing in a part of space-time you no longer inhabit. Perhaps parallel selves are simply an extension of this temporal structure. Just as past you and present you are connected but distinct, so are you and your quantum branches, threads of a larger pattern, moments in a more complex structure, pieces of something that can't be reduced to a single simple self. This doesn't solve the puzzle of identity, but it shifts the question. Maybe the issue isn't whether parallel selves are really you. Maybe it's about recognizing that identity itself is fluid, context-dependent, something that comes in degrees rather than absolutes. And in a branching universe, that fluidity just becomes more literal. Let's turn now to a question that might seem abstract but has surprising moral weight. If our actions create branches where we make different choices, do we bear any responsibility for what happens in those other branches? At first, the answer seems obvious. No, you can't control what happens in other branches. You can't even observe them. You experience only one thread of reality. Why should you be responsible for versions of yourself you'll never meet, making choices you'll never know about, in worlds you'll never perceive? But let's probe a little deeper. Suppose you're faced with a decision, a genuinely difficult one where quantum randomness in your neural processes might tip you toward different outcomes. In some branches you choose generously, in others selfishly. If many worlds is true, that both versions of you will exist, both futures will unfold, does that knowledge change your moral calculus? Are you, in some sense, responsible for the entire ensemble of branching outcomes, not just the one you'll subjectively experience? Some philosophers have argued yes. If you know your action creates branches, and in some branches your choice causes harm, then you're morally implicated in that harm, even if you don't experience it directly. It's analogous to setting in motion a series of events that will hurt someone else. Even if you don't witness the outcome, you're still responsible. But others push back. Responsibility requires agency, and you don't have agency over which branch you end up in. That's determined by quantum randomness, not by intention or will. You choose an action, and the branching follows inevitably from the quantum structure of reality. Blaming you for what happens in branches you can't control would be like blaming you for the laws of physics. There's also a practical consideration. If you're responsible for all branches, and every choice creates branches where you make different choices, then you're simultaneously responsible for every possible action, good and bad, generous and cruel. That seems to dissolve responsibility entirely. If you're accountable for everything, you're accountable for nothing. Perhaps a middle position is more reasonable. You're responsible for the actions you take in this branch, the one you experience, where your intentions and choices directly shape outcomes. The other branches are real, in the many worlds framework, but they're not your moral domain. You can't help them. You can't harm them. They unfold according to their own logic, shaped by versions of you that are, in the moment of branching, effectively different people. This brings us back to the importance of local experience. Even in a branching cosmos, ethics remains grounded in the immediate, the relational, the subjective. You're responsible to the people around you, in this thread of reality, for the consequences of your choices as they unfold here. The fact that other versions of you might be making other choices elsewhere doesn't dilute that responsibility. If anything, it emphasizes it. This moment, this choice, this relationship, these are the domains where your agency operates. These are where your ethics matter. Parallel worlds, if they exist, don't create a moral labyrinth. They simply add a layer of ontological complexity to a structure that was already, in its own way, multiple. The multiverse just extends that insight. You act locally, within the sphere of your influence, guided by intention and care, and that's enough. So after all this speculation about choices, identity, responsibility, alternate paths, what does it mean for how we live, for how we hold ourselves, our histories, our futures? Perhaps the greatest gift the multiverse hypothesis offers, if we choose to accept it, isn't knowledge but perspective, a way of holding our lives a little more lightly, with a little less clinging to the illusion that there was only one right path and we might have missed it. Think about regret. So much of our suffering comes from dwelling on decisions we wish we'd made differently, the relationship we ended, the opportunity we declined, the words we spoke or didn't speak. We replay these moments endlessly, imagining how things might have been better if only we'd chosen otherwise. But what if, in some branch of reality, we did choose otherwise? What if every possibility was actualized somewhere, and the path we're on is just one among many equally real threads? This doesn't erase the consequences of our choices. As we discussed, we still experience this particular life, with its particular joys and sorrows, shaped by the decisions we actually made. but it might soften the sharpness of regret. The unlived life isn't lost, it's being lived by a version of you in a parallel branch. Nothing was entirely sacrificed. Every fork in the road led somewhere. Of course, this cuts both ways. If you feel satisfied with your choices, the knowledge that other versions of you made different ones might introduce doubt. Maybe the life you didn't live would have been better. But here's where acceptance becomes crucial. You can't know what happens in other branches. You can't compare outcomes. You can only live the life you have, attend to the present moment, make choices based on the information and values available to you now. The multiverse, if it exists, doesn't give you access to other lives. It doesn't let you trade this experience for another. What it does is remind you that reality is larger than any single narrative, that existence is more abundant than scarcity thinking suggests, that the universe has room for all possibilities, and perhaps that's liberating. Perhaps it's comforting to think that, in the grand structure of reality, nothing is lost. Every potential is realized. Every story finds its telling. The cosmos is not a place of winnowing and elimination, where most possibilities die unrealized. It's a place of unfolding proliferation, where everything that can happen does happen, somewhere, in some form. This doesn't mean your choices don't matter. We've established that they do, but it means they matter in a context of abundance rather than scarcity. You're not responsible for choosing the single correct path among infinite wrong ones. You're simply choosing which path you'll walk, knowing that the others are being walked as well. There's a kind of peace in that if you can find it, a release from the tyranny of what if, an invitation to inhabit this moment, this life, this particular thread of experience, without constantly measuring it against imagined alternatives. Whether the many worlds interpretation is true or not, this perspective might be worth cultivating. The idea that reality is generous, that existence is abundant, that there's room for all the stories, that's a lens through which life can feel less constricted, less burdened by the weight of paths not taken. And on a quiet night, settling into stillness, that perspective might help the mind rest a little easier. As we move toward the final stretch of our journey, let's confront a fundamental limitation, not of our technology or our theories, but of reality itself. There are boundaries to what can, even in principle, be known, and some of those boundaries are absolute. Consider the cosmic horizon. We've mentioned it before, but let's sit with it more carefully. Light travels at a finite speed, about 300,000 kilometers per second. In the 13.8 billion years since the Big Bang, light has traveled a certain maximum distance. Allowing for cosmic expansion, the edge of the observable universe is about 46 billion light-years away, in any direction. Beyond that horizon lies more space, almost certainly, probably infinite space, but we can never observe it, not because our telescopes aren't good enough, but because light from those regions hasn't had time to reach us yet. And as the universe continues expanding, in fact accelerating in its expansion due to dark energy, distant regions are receding from us faster than light can travel. The observable universe is not growing to encompass more of the total universe. It's shrinking in a sense. Regions that we can currently see will, eventually, redshift beyond detectability, slipping over the horizon forever. This means there's a fundamental boundary to information. Events occurring right now beyond our cosmic horizon are causally disconnected from us. No signal can ever reach us from there. No influence can propagate. For all practical and theoretical purposes, those regions might as well be separate universes. If level 1 multiverse is real, if space extends infinitely and contains infinite duplicate regions, we can never confirm it through observation. Those other Earths, those other versions of you, lie far beyond any possible horizon. They're real, if the math is right, but forever inaccessible. The same applies to level 2, the bubble universes of eternal inflation. If our universe is one bubble among countless others, separated by regions of space still undergoing exponential inflation, then no signal can cross from one bubble to another. The intervening space expands faster than light. The bubbles are sealed off from one another, not by walls but by the geometry of space-time itself. And in many worlds, quantum branching creates a different kind of horizon, decoherence. The interaction of quantum systems with their environments entangles branches in ways that make interference between them vanishingly unlikely. The branches exist, in the mathematics, but they don't interact. They can't observe one another. They're separated not by space, but by the structure of the quantum state. These aren't temporary limitations. They're not problems to be solved with better instruments or cleverer experiments. They're built into the fabric of reality. There are regions of the cosmos, and perhaps entire categories of existence, that we are fundamentally prevented from accessing. This might feel frustrating. Humans are curious creatures. We want to know. We push against boundaries. But perhaps there's also something humbling and even beautiful in recognizing limits. The universe doesn't owe us complete knowledge. It doesn't structure itself for our epistemic convenience. And in that recognition, we might find a kind of wisdom. The wisdom to pursue knowledge where it's available, to speculate carefully where direct evidence is impossible, and to accept that some questions might remain forever open, hovering at the edge of the knowable, inviting wonder without offering resolution. Let's stay with this theme of limitation and consider another barrier, one rooted not in the structure of space, but in the nature of observation itself. We've discussed how quantum mechanics works. Systems exist in superposition until measured, at which point, according to the Copenhagen interpretation, the wave function collapses, or, according to many worlds, it branches, with each outcome realized in a different thread of reality. But here's the crucial point. If branching occurs, you can't observe the other branches. This isn't a technological limitation. It's a consequence of how decoherence works. When a quantum system interacts with its environment, including observers and measuring devices, it becomes entangled with that environment in ways that make different outcomes distinguishable. Each outcome corresponds to a different quantum state of the entire system, including the observer. You, as an observer, become part of one branch. Your measuring device, your brain, your memories, all of these exist in a superposition across branches, but each branch contains a version of you that experienced only one outcome. Decoherence ensures that these branches don't interfere with one another. The quantum phases that would allow them to interact become so complex, spread across so many environmental degrees of freedom, that recombining them is practically impossible. It would require reversing the entropy of an enormous number of particles, a feat so unlikely that it might as well be impossible. So even if many worlds is true, you'll never perceive evidence of it directly. You'll never see the version of yourself in another branch. You'll never receive a signal from a parallel timeline. The branching structure is encoded in the universal wave function, but from within any single branch, reality appears singular. This raises a question. If a structure exists in the mathematics but can never be observed, in what sense is it real? Some physicists argue that mathematical existence is sufficient. If the equations predict something, and the equations are confirmed by experiment in other domains, then we should take their full implications seriously, even the unobservable parts. Others argue that reality should be identified with what can, at least in principle, be measured or experienced. There's no consensus answer, but the question highlights a deep tension in how we think about reality. Is the universe fundamentally mathematical, with physical existence being just one manifestation of abstract structure? Or is physical existence primary, with mathematics being a tool we use to describe it? The many worlds interpretation and multiverse theories more broadly push this question to its limit. They ask us to believe in realities we cannot observe, based on the internal logic of theories that work well in observable domains. Perhaps the most honest response is to acknowledge the uncertainty. We don't know what criteria are sufficient for reality. We don't know whether unobservable branches of a wave function deserve the same ontological status as observable particles. We're navigating territory where science blends with metaphysics, where our intuitions offer little guidance. But there's something fitting about that. Consciousness itself is a mystery, a subjective, private experience that can't be fully observed from the outside. Perhaps it's appropriate that the structure of reality, at its deepest level, includes aspects that are similarly private, accessible only from within particular perspectives, forever hidden from the view of others. We are embedded in the universe, not external to it, and from that embedded position, some truths might remain forever, just beyond reach. Having acknowledged the limits of observation, let's consider why so many physicists pursue multiverse theories despite those limits. What drives scientists to spend careers developing ideas that might be untestable? One answer is mathematical beauty. This might sound subjective, even frivolous, but beauty has been a surprisingly reliable guide in physics historically. Consider Paul Dirac's equation, formulated in 1928, to describe electrons relativistically. The equation had an unexpected feature. For every solution representing an electron, there was another solution with opposite charge. Dirac initially thought this might correspond to protons, but the mathematics insisted the antiparticle should have the same mass as the electron, not the much heavier proton. In 1932, the positron, the electron's antiparticle, was discovered, exactly as Dirac's equation predicted. Dirac had followed mathematical beauty into uncharted territory and found reality waiting there. Or consider Einstein's field equations of general relativity. They're elegant, symmetric, conceptually satisfying, and they predict black holes, gravitational waves, the expansion of the universe, phenomena that seemed fantastical when first proposed but have since been confirmed. Time and again, physicists have found that equations possessing certain aesthetic qualities, symmetry, simplicity, elegance, tend to describe nature accurately. The universe, it seems, favors mathematical beauty, or perhaps it's that human minds, shaped by evolution in a mathematical universe, have learned to recognize patterns that reflect deep truths. Many worlds has this aesthetic appeal. It doesn't require adding collapse postulates to quantum mechanics. It doesn't introduce arbitrary divisions between quantum and classical realms. It simply takes the Schrödinger equation seriously and follows its implications. The result is ontologically extravagant, infinitely many branches, but mathematically minimal. It's a theory with few assumptions and vast consequences. Similarly, eternal inflation emerges naturally from the equations governing cosmic inflation. It wasn't designed to produce multiverses. Multiverses fell out of the math when physicists worked through the implications rigorously. String theory, for all its challenges, possesses extraordinary mathematical richness. The same equations that predict extra dimensions and branes also unify gravity with quantum mechanics, a feat that no other framework has accomplished, even partially. So when physicists pursue these ideas, they're not just speculating wildly, they're following a method that has proven fruitful before. Find the most beautiful mathematics that fits the data, then trust it even when it predicts things you can't immediately observe. But beauty alone isn't proof. History also contains examples of elegant theories that turned out to be wrong. Ptolemaic astronomy, with its perfect circles and epicycles, was geometrically beautiful, but ultimately incorrect. Newtonian physics is elegant and still useful, but fundamentally incomplete. So where does that leave us? Recognizing perhaps that beauty is a hint, not a guarantee. It's a reason to take an idea seriously, to explore its implications, to search for indirect evidence, but it's not sufficient justification for belief. The physicists developing multiverse theories understand this. They're not claiming certainty. They're mapping conceptual territory, exploring possibilities, developing frameworks that might eventually make contact with observation, or might remain forever in the realm of elegant speculation. And there's value in that work, even without definitive answers. It expands our imagination. It reveals new connections between ideas. It pushes the boundaries of what we can conceptualize. And occasionally, beauty-driven speculation finds itself confirmed by reality. Perhaps one day, multiverse theories will transition from speculative to established, or perhaps they'll remain beautiful ideas, mathematically consistent but empirically unverifiable. Either way, the pursuit has meaning. We're nearing the end of our journey, and it's worth pausing to acknowledge something we've circled around repeatedly. We don't know. We genuinely, honestly don't know whether parallel worlds exist. This might feel unsatisfying. We've spent hours exploring ideas, following threads of logic, considering evidence and implications, and the conclusion is, but perhaps uncertainty is exactly the right place to arrive. Perhaps it's the most honest position to hold. Science progresses through uncertainty. The questions that drive research forward are precisely the ones we don't yet know how to answer. If everything were settled, there would be nothing left to explore. Uncertainty isn't a failure, it's the engine of inquiry. And beyond science, uncertainty is a fundamental condition of existence. We don't know what tomorrow will bring. We don't know the full consequences of our choices. We don't know what happens after death. We live our entire lives embedded in mystery, making decisions based on incomplete information, constructing meaning in the absence of guarantees. Parallel worlds simply extend that uncertainty into a new domain. We're already comfortable, or at least familiar, with not knowing countless things. Whether other versions of ourselves exist in unreachable branches of reality is just one more item on a very long list. But there's a difference between different flavors of uncertainty. Some uncertainties are temporary. Questions we'll eventually answer with better instruments or more data. Others are practical, things that could be known but that we lack the resources to investigate. And some are fundamental, boundaries built into the structure of reality, questions that might remain forever unanswerable. Parallel worlds fall, for now, into the third category. They might be real, they might not, we might never know for certain, and that's okay. There's a certain freedom in accepting this. It releases us from the burden of needing to have an answer, of choosing one interpretation and defending it against all comers. We can hold the ideas lightly, appreciate their beauty and implications, consider what they might mean for how we see ourselves without committing to certainty. This isn't relativism or intellectual laziness. It's epistemic humility. It's recognizing the difference between what we know, what we suspect, what we speculate, and what we wish. And it's being honest about which category any given idea falls into. Parallel worlds are, at present, speculative, grounded in serious physics. Yes, consistent with verified theories. Yes, but not proven, not directly observed, not confirmed beyond reasonable doubt. So we wonder, we explore, we follow the mathematics, we search for evidence, we construct thought experiments, and probe the boundaries of the knowable, and we accept that, at the end of all this inquiry, the ultimate answer might remain just beyond our grasp. That's not a failing, that's the human condition. We are small, finite, embedded in a cosmos vastly larger and older than ourselves. We do our best to understand, knowing that our understanding will always be partial, provisional, limited by our perspective and our tools. And yet we try, we ask, we wonder, because the questions themselves have value, regardless of whether we ever find definitive answers. And in a quiet moment settling toward rest, perhaps that's enough. So let's conclude this chapter and prepare for our final turn toward rest by celebrating the question itself. What is it about parallel worlds that captivates us? Why does the idea resonate, even for those who remain skeptical of its truth? Perhaps it's because the question touches something deep in the human experience, our sense that life is larger than any single story, that possibilities hover around us constantly, that the boundary between what is and what might have been feels thinner than we usually acknowledge. We live with counterfactuals, we imagine alternatives, we construct narratives about paths not taken, choices we didn't make, versions of ourselves we might have become. This imaginative capacity is part of what makes us human. It allows us to plan, to learn from hypothetical scenarios, to empathize with others by imagining their perspectives. Parallel worlds give ontological weight to this imaginative capacity. They suggest that the alternatives we envision might not be mere fictions, but real possibilities unfolding in regions of reality we can't access. They dignify our sense that life could have been otherwise, not just in our imaginations but in the actual structure of the cosmos. There's also something humbling about the question. If parallel worlds exist, then our experience is just one thread in an incomprehensibly vast tapestry. We're not the center of reality. We're one perspective among countless others, all equally valid, all equally embedded in the larger structure. And yet, paradoxically, the idea also affirms the value of our particular experience. If every possibility is realized, then this moment, the one you're living right now, is unique in its particularity, even if it's not unique in its existence. Your life, your choices, your subjective experience, these are real and significant within their context, regardless of what's happening in other branches. The question of parallel worlds also invites awe. The universe we're discovering is stranger than we imagined. Quantum mechanics defies intuition, space-time curves. The cosmos might extend infinitely, and reality might be structured in ways that exceed our most ambitious speculations. That strangeness is worth appreciating. We've grown accustomed to the ordinariness of daily life, to objects being where we expect them, to cause and effect unfolding predictably. But underneath that veneer of normalcy, nature operates according to principles that are deeply, beautifully, irreducibly weird. Parallel worlds, whether real or not, are a reminder of that weirdness. They're an invitation to hold our assumptions lightly, to remain open to possibilities that challenge our inherited frameworks, to approach reality with curiosity rather than certainty. And that invitation has value in itself. Even if we never confirm whether parallel worlds exist, the act of asking the question expands us. It makes us think more carefully about identity, choice, existence, knowledge. It connects us to the long tradition of humans wondering about the nature of reality, reaching beyond the immediately visible, searching for deeper patterns and larger contexts. So as we prepare to return from this speculative journey, perhaps the greatest gift isn't an answer. It's the reminder that reality is vast, strange, and worthy of wonder, that questions matter as much as answers, and that the capacity to ask, to imagine, to explore ideas at the edge of the knowable, that's a profound and precious part of what makes us human. And now, gently, let's begin the return. We've traveled far, across quantum landscapes, through cosmic horizons, into philosophical territories, where identity and choice take on strange new dimensions. But wherever the mind has wandered, the body has remained here, in this room, on this planet. In this particular branch of reality, if indeed reality branches, feel the surface beneath you, the weight of your body however it's resting, the temperature of the air, the ambient sounds, near or distant, that make up the texture of this moment. This is where you are. This is the universe you inhabit, not in abstraction, but in immediate, tangible presence. Whether or not parallel worlds exist somewhere beyond perception, this world is undeniably real. The breath moving in and out of your lungs, the thoughts drifting through your mind, the subtle sensations that make up your felt experience of being alive right now. These aren't contingent on theoretical physics. They're simply here, irreducible, present. There's something grounding about returning to the immediate after a journey through vast abstractions. The cosmos might extend infinitely in space, eternally in time, multiply across quantum branches and cosmic bubbles, or it might not. But either way, this moment exists. You exist. The particularity of your experience, the specific configuration of sensations, thoughts, memories that make up your now, is real. Perhaps that's the ultimate anchor. Not certainty about the structure of reality, but the undeniable fact of experience itself. The universe, whatever its full extent, includes this. The feeling of lying quietly, thoughts slowly settling, awareness softening at the edges, the day's urgencies gradually releasing their grip. And maybe that's enough. Maybe the search for grand explanations, for cosmic contexts and ultimate frameworks can rest for a while. Not because the questions aren't fascinating, they are, but because there's also a completeness in the simple fact of being, here, now, without needing to know how it all fits together. So let the theories drift. Let the parallel worlds, if they exist, unfold without your attention. Let the quantum branches and bubble universes and mathematical structures continue their existence, real or imagined, beyond the horizon of immediate concern. This moment doesn't require them. This breath doesn't need cosmic validation. You are here, that's sufficient. As you settle deeper, consider for a moment the sheer unlikeliness of your existence, whether we're talking about one universe or many. The atoms that make up your body were forged in stars that died billions of years ago, scattering their enriched material into space where it eventually coalesced into new solar systems. The planet you live on formed in a region where conditions happen to be right, not too hot, not too cold, with liquid water and a protective atmosphere. Life emerged through a process we still don't fully understand, then evolved over billions of years through countless branching paths, eventually giving rise to creatures capable of consciousness, language, wonder. And then, out of all the possible combinations of genetic material, you came to be. This particular configuration of traits, temperament, capacity, born in this era, on this world, with opportunities to learn, to think, to contemplate questions about the nature of reality itself. The improbability is staggering, and it doesn't matter whether we're one universe among many, or the only universe there is. The fact remains, you exist. Against all odds, the conditions aligned in just the right way for your particular existence to occur. If we're in a multiverse, then perhaps there are countless other versions of these conditions, countless other beings asking similar questions. But that doesn't diminish the extraordinary nature of this instance. This you, this moment, this capacity to experience and reflect and wonder. There's a kind of gratitude that can arise from contemplating this improbability. Not gratitude directed at anything in particular, but a general sense of appreciation for the sheer fact of being, for having this window of awareness, this brief span of time to participate in the universe's unfolding, to witness beauty, to connect with others, to explore ideas at the edge of understanding. You didn't ask to exist. None of us did. We simply find ourselves here, embedded in a cosmos whose origins and extent remain mysterious. But here we are, and whatever comes next, whatever lies beyond the boundaries of our knowledge, we have this, the gift of now. So breathe. Feel the quiet wonder of existence itself, not the grand cosmic structures, not the theoretical frameworks, but the simple, immediate fact of being alive, aware, present. It's improbable, it's temporary, it's precious beyond measure, and for this moment at least, it's yours. We've spent this time exploring questions about parallel worlds, quantum mechanics, the structure of reality. We've encountered ideas that challenge our assumptions and stretch our imaginations, and we've acknowledged repeatedly that many of these questions remain unanswered, perhaps unanswerable. But as we approach the threshold of sleep, it's worth recognizing that not knowing isn't a problem to be solved. It's a condition to be accepted, and there's a certain comfort in that acceptance. Think about how much we don't know, not just about parallel worlds and quantum mechanics, but about everything. We don't know why there's something rather than nothing. We don't know where consciousness comes from or where it goes. We don't fully understand time, causation, the origin of physical laws. We don't know if reality is fundamentally material or mathematical, or something else entirely. We don't even know if the questions we're asking are the right questions, or if reality operates according to principles we haven't yet imagined. And yet we continue. We wake each day and navigate the world with confidence despite this vast sea of ignorance surrounding our small island of understanding. We make choices, form relationships, find meaning, experience beauty, all without needing definitive answers to the deepest questions. Mystery, it turns out, is compatible with living well, perhaps even necessary for it. If everything were known, mapped, explained, what would be left to wonder about? What would drive curiosity forward? What would keep the universe feeling alive, dynamic, full of possibility? Science advances not in spite of mystery, but because of it. Every answer reveals new questions. Every boundary crossed unveils new horizons. The unknown isn't emptiness. It's the space where discovery lives, where imagination plays, where the next insight waits patiently to be found. So as your thoughts begin to dissolve, as the urgency to understand fades into the softness of approaching sleep, let the mysteries remain. You don't need to solve them. You don't need to have an opinion about quantum interpretations, or multiverse theories, or the ultimate nature of existence. It's enough to have wondered, to have followed these ideas with curiosity and openness, to have spent this time contemplating questions that have no easy answers, and finding in that contemplation not frustration, but a kind of peace. The universe will keep its secrets, and that's okay. You can rest in the mystery, let it hold you gently, trust that not knowing is a perfectly fine place to be. Release the need for certainty, let the questions drift away, and find comfort in the simple fact that some things can remain forever unknown. And now, finally, let yourself drift. Sleep, in its way, is a journey to another reality, not parallel worlds in the physicist's sense, but a different state of consciousness, one where logic loosens, where time becomes fluid, where impossible things seem natural and narratives shift without explanation. Every night you make this journey, you leave behind the waking world with its solid objects and causal chains and persistent sense of self, and you enter the dream realm. There you might fly or find yourself in places that don't exist or encounter people you've never met. The laws that govern waking experience suspend themselves, and for a time, that other reality is the only reality you know. Perhaps dreams are their own kind of parallel world, not separate universes in space, but separate modes of being accessible only through the dissolution of ordinary consciousness. We spend a third of our lives there, yet we remember so little. The dream you and the waking you share the same brain, the same body, yet they experience reality in profoundly different ways. And then, deeper than dreams, there's the state beyond them, the deep sleep where awareness itself seems to pause. Where are you then? Who are you when there's no experience, no narrative, no sense of passing time? You go away, in some sense, and then return, hours later, often with no memory of the gap. It's a small mystery, repeated nightly, a temporary disappearance and reappearance, a journey out and back. So as you feel yourself approaching that threshold now, let it be gentle. Let the boundary between waking and sleeping blur softly. Let thoughts slow and dissolve like clouds dissipating in a clear sky. Let your body sink into complete rest, releasing any remaining tension, any lingering concerns. The questions we explored tonight will still be there tomorrow, if you want to return to them. The universe, in all its strangeness and vastness, will continue unfolding. But right now, there's nothing you need to figure out, nothing you need to hold on to, just this, the gentle drift towards sleep, the body's natural wisdom calling you into rest. Perhaps in some branch of reality, another you is still awake, still wondering, still thinking about parallel worlds and quantum mechanics. But here, in this branch, in this moment, it's time to let go. So breathe slowly. Feel the weight of your body fully supported. Notice how easy it is to simply rest, to allow consciousness to soften and blur, and eventually fade into the particular mystery of sleep. You've traveled far tonight, and now you're coming home to the quiet, to the dark, to the simple peace of being. Rest well,